I'm Markarinis, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Last time, we counted the number of ways to move from the top left corner to the bottom right corner of a 20 by 20 grid using only rightward and downward motion. We solved that problem in Prolog, and here's the code we used to do it. Today, I want to talk some more about how logic programming actually works on the back end and how Prolog goes about evaluating your code. This one is going to be a bit more theoretical in some places than a lot of my other videos. As we've discussed, a Prolog program consists of facts and rules. Once we've stated the facts and rules of our model, we ask the Prolog system a question. We might ask it a question in the interpreter, or we might implicitly ask it a question by providing a main predicate with no conclusion in the source code itself. That question we've asked is our goal. To solve the goal, Prolog performs a depth-first search of the facts and rules it knows. Every time we encounter something whose conclusion involves the same predicate as our goal, we attempt to unify the terms present in the conclusion with those in the goal. If unification succeeds, then we follow through and try to recursively prove the hypotheses of our rule, if there are any. Naturally, a fact stated on its own has no hypotheses, so it's true from the moment unification succeeds. Unification is the process of checking whether two terms can be made to look the same. This concept isn't just used in logic programming, it's also implicitly used in any programming language that supports type inference in order to check whether the required type of a term is compatible with the inferred one. At its most basic level, unification is simply an equality check. If we want to check whether two terms alpha and beta unify, the first thing to do is to check whether they're equal. If so, then they unify. But that's not quite good enough. In Prolog, if we ask whether the predicate p of 1 is true, and we have a fact that states that p of x is true, then the fact should be interpreted to mean that p of x is true for all x. Hence, p of 1 is true as 1 is a possible value of x. Stated in terms of unification, if one of the terms is a variable, then the two also unify, and the unification process remembers that the variable is bound to the value it just unified with. For example, suppose we try to unify p of 3, 3 with p of x, x. First, we observe that both sides are invocations of the same compound term p with two arguments, so unification is possible if the arguments match up. Next, we try to unify 3 and x. One of the two sides is a variable, so we simply make a note that x must be equal to the number 3 and move on. When we encounter the second argument, we find again that 3 and x must unify. Unification succeeds in both cases, so we terminate successfully with a note that x is equal to 3. Now let's try the same thing with p of 3, 4 and p of x, x. The first step proceeds as before. We have a compound term with two arguments, so we try each argument in turn. First, we unify the first arguments, 3 and x, as before. We make a note that x must be 3, then we unify the second arguments, those being 4 and x. Normally, a variable and a term would unify, but we already know that x must be equal to 3, so we can't also claim that x is equal to 4. Unification fails. If unification succeeds, we proceed forward. But what happens if unification fails? To answer that, we need to talk about choice points. In Prolog, a predicate can be true any number of times, potentially with different instantiations of its free variables. We've already seen examples of this when we were talking about the Harry Potter family tree. The predicate sibling Ginny Weasley, x succeeded several times, once for each of the Weasley siblings. In the REPL, we can force Prolog to identify all of the different instantiations of a variable that make a predicate true by hitting the semicolon key. Internally, when Prolog is performing its truth search and finds a fact or rule that unifies successfully, if there's a possibility of another fact or rule succeeding, then it leaves behind a choice point. A choice point is a note to the interpreter that, if we need to evaluate other ways this fact may be true, one place to start looking might be this choice point. When unification fails, Prolog backtracks to the most recent choice point and continues its search from there. If unification succeeds, but we ask for all solutions, for instance if we're running in the built-in REPL, then we also backtrack to go look for additional solutions. If every choice point is exhausted and we still haven't found a solution, then we can conclude with certainty that the goal is false. Let's see a concrete example. For now, we'll just work with facts and not any rules. Here we have a list of the first 7 United States presidents. We've also taught Prolog the years they were born and the political parties they were affiliated with. These are the facts of our system, and Prolog remembers them in the order we wrote them here. Now let's ask Prolog for all of the presidents who were affiliated with the Democratic Republican Party. Our goal is to make these two statements true simultaneously. Our only free variable is p. Prolog proceeds in order. First, we need to find a president who unifies with p. Since p is a variable and we don't have any bindings for it yet, it will happily unify with anything. The first fact we have for the president predicate is Washington. So we unify p and Washington, and we've successfully made the president predicate true. In the process, we note that there are other president clauses, so we leave behind a choice point for the predicate. If we ever have to backtrack, this is a good place to start looking. Now that we have that p is Washington, we also want to make party p, Democratic Republican true. There are several party rules, but none of them have a first argument which unifies correctly with Washington. So our attempt to prove the goal, party of Washington, Democratic Republican, fails. We have a choice point that we made earlier, so that means we can backtrack and continue our search from there. We backtracked to before P was equal to Washington, so we have to erase that binding. Let's try the second president, Adams. Now P is bound to Adams, and we want to prove party Adams, Democratic Republican. We have a rule for party whose first argument is Adams, but its second argument doesn't match, so again, we failed. We backtrack to our choice point and try P equals Jefferson. In this case, we succeed since party Jefferson, Democratic Republican is a fact. There's still a choice point, so we can ask Prolog to continue searching by entering the semicolon key, and it will find the others. Madison, Monroe, and Quincy Adams. If we ask it to search again after Quincy Adams, the search will fail, since our choice point will produce Jackson, who is not a Democratic Republican, and then we'll run out of presidents to try. Prolog affords us some ability to control the choice points in our program. The simplest way to do so is with the once predicate. The once predicate takes a single argument and treats it as a goal, with the caveat that it will only search for one solution and then report failure beyond that point. Basically, as soon as the goal inside of once succeeds, the predicate calls all choice points made after the beginning of the once call. If we wrap our previous goal in once, then rather than succeeding 4 times, it will succeed only once, with P equal to Jefferson, and then stop. Now is a good time for a brief aside on terminology. If a predicate is guaranteed to succeed exactly once, we call that predicate deterministic. If a predicate succeeds at most one time, we call that predicate semi-deterministic. If a predicate is guaranteed to have at least one solution but might succeed multiple times, we call it multi-deterministic. Finally, if none of these labels apply and a predicate can succeed 0 or more times, we call it non-deterministic. Under these rules, the once predicate takes non-deterministic predicates and forces them to be semi-deterministic, and it takes multi-deterministic predicates and forces them to be deterministic. Once is actually not the most primitive choice point construct in Prolog. The most primitive construct is the cut. The cut is written as a single exclamation mark. When the Prolog interpreter encounters a cut in the hypothesis of a rule, the cut succeeds, but has the side effect of calling all choice points constructed since the beginning of the current predicate. That's a mouthful. Let's see a practical example of why we'd care about this. Last time, we wrote a predicate that behaved like the built-in Prolog length predicate for lists. Specifically, it took 2 arguments, a list and an integer, and was true if and only if the list had length equal to the integer argument. This is the predicate we wrote, slightly modified to work with actual Prolog lists rather than the cons term we made up last time. Our first fact concludes that the length of the empty list is 0. Then we had a rule that stated that if the length of the tail of the list is y, and our integer argument x is the successor of y, then the length of the whole list, with one more element in front, must be x. This predicate works and can be used in a couple of ways. First, if we supply both arguments, Prolog succeeds once if and only if the list actually has the length we told it does. Second, we can leave the latter argument blank, and Prolog will calculate the length of the list and give it to us. Let's see what happens if we feed Prolog a length, but leave the list argument as a variable. The built-in Prolog length predicate works in this case, producing a list of that many elements, each of which is an unbound independent variable. But if we try our predicate in this way, Prolog actually gives us the right answer, but then as soon as we start backtracking, we get into an infinite loop of some kind. Let's trace our program and see why that is. Our goal is list length L, 2. We have 2 possible clauses that can be used to prove this, our base case and our recursive one. The base case fails since 2 is not equal to 0, and our base case has a 0 as its second argument. So we need to unify list length L, 2 with the conclusion of our recursive rule. The second argument unifies easily, with the note that the length variable x must be equal to 2. For the first, we need L to unify with the list cons ht. This also isn't a problem. Since L has no current value, we can simply bind it to our cons cell and move on. At this point, we know that x is bound to 2 and L is bound to h cons t. The variables h and t exist but are unbound. But this is a rule, which means it has hypotheses. So if all of this is going to work out, we need to prove our 2 hypotheses, list length t, y, and successor y, 2. We recursively try to prove list length t, y. If we try our first fact, list length empty list, 0, we can conclude that t is the empty list and y is 0. Then we try to prove successor of y, x, with y equal to 0 and x equal to 2. This fails since 0 plus 1 is not 2, so we backtrack. We backtrack to the choice point list length t, y, so we forget our bindings for t and y. If t is the empty list and y is 0, then we fail, so we move on to the second case. We want to unify t, y with the arguments to our recursive rule. But because of variable scoping, the t appearing in our rule is not the same t we have right here. So we're going to rename the variables appearing in our rule to something that won't conflict with the variables we already know things about. This is called alpha conversion. Now we want to unify t, y with cons h1, t1, x1. Unification succeeds, and we get a few more notes, namely that t is bound to cons h1 t1, and y is identified with x1. But now, as per our hypotheses, we have to prove list length t1, y1. If we try our first fact, we can conclude that t1 is the empty list, y1 is 0, and now we have to test that successor y1, x1 is true. y1 is 0 and x1 is unbound, so we conclude that x1 is 1. This also tells us that y is 1. Now, we keep going up the call stack and need to show from our original rule that successor y, x is true. X is bound to 2 and y is bound to 1, so this succeeds since 1 plus 1 is equal to 2. Now we have our first solution, and it's of this form. Once we simplify all of our substitutions, we get a prettier representation as L equals h, h1. Ideally, this is our only solution, but unfortunately, Prolog won't stop here. Prolog will keep trying successively longer lists in the hopes that if we apply the successor operation enough times, we might magically loop back around to 2 at some point. Mathematically, you and I both know this is nonsense, but Prolog doesn't. It will keep trying successively larger numbers forever, never realizing that it keeps getting further and further away from its goal of 2. We could attempt to fix this by swapping the order of the successor and recursive calls. This works for the example input we just gave, since Prolog's successor predicate is smart enough to understand that there is no number whose successor is 0. But this causes another problem. If we call the predicate the usual way with a list and an unbound variable for length, then Prolog complains that I've asked it to calculate a successor, but haven't actually given it any numbers. What we really want is a predicate that knows which order to evaluate the rules in, depending on which variables are bound. Prolog has a predicate that's true when a variable is not bound to a concrete value, and that predicate is called var. We can get closer to what we want by writing this. The first clause is our base case as always. The second is a clause that can only continue if x is a variable. If that's the case, then we recurse on our list length predicate first to get a value for x, and only afterward do we check the successor. Finally, our last case does the successor check first, and then the length check. This gets us close, but it still has one problem. The second clause only runs if x is a variable, but the third one will also try to run in that case. Once we've gotten our first solution, the second clause will finish, we'll hit the choice point for it, and we'll move on to the third clause, which will produce a Prolog error, since again, we have two variables being passed to the successor predicate, and Prolog can't calculate it. What we really want to do is this. If the second clause matches because x is a variable, we want to force Prolog to commit to that branch and to delete the choice point that would cause it to go to the third one. If we place a cut right after the var check, Prolog will delete that choice point. The cut succeeds, as it always does, and proceeds onward with the current branch. Any branching that occurs after this point is still fair game, but we'll never backtrack to this particular stack frame again, because the cut has forced us to commit to the variable bindings in place right now. This version of the length predicate can, at long last, be called any way we like. If we pass it 2 arguments, it succeeds semi-deterministically. If we pass it a list, it succeeds deterministically with the length. If we pass it a length, it succeeds likewise deterministically with a list of that length. And, as an added bonus, if we pass 2 independent variables, Prolog will start enumerating all of the ways this can be true. Starting with L equals the empty list and x equals 0, then L a list of length 1 at x equals 1, and so on. In the ideal world, every single predicate we write would be like this. Every single argument can be bound or unbound, and any combination just works intuitively. As you've seen so far, though, that's not always a realistic expectation. There are always going to be some predicates that have an inherent direction to them, where some arguments are intended as input, and some are intended as output. To help identify such predicates, the official Prolog documentation follows some conventions for labeling arguments. Every argument in the Prolog documentation is preceded by a sigil indicating its mode. The first mode is a question mark, or partial term indicator. This is our ideal world scenario. An argument with the question mark indicator can be passed bound to a value, or it can be left blank for the predicate to fill in as it chooses. Our length predicate, like the built-in one, takes both of its arguments with the question mark indicator. Note that the question mark is not a blank check to leave all arguments unbound, but merely an indicator that each argument, when viewed in isolation, can be unbound. For instance, the 2-argument successor predicate from the standard library takes both arguments as question mark arguments. We can leave either argument blank and infer it from the other, but if we leave both arguments blank simultaneously, Prolog will complain. For predicates which have inputs and outputs, the input arguments will be marked with a plus sign sigil and the outputs with a minus sign sigil. A plus sign or input argument must be instantiated to a term within the domain of the predicate. Generally, leaving a completely unbound variable or underscore in the place of such an argument will produce an error. The open predicate, which opens a file for reading or writing, takes the file name and mode arguments as inputs. If you try to call open with an unbound variable as the file name, Prolog will understandably complain because it doesn't know which file to open. Output arguments, likewise, are marked with a minus sign. An output argument will be unified with the result of some computation. The div mod predicate is a built-in predicate which takes 4 arguments. the dividend, divisor, quotient, and remainder. It performs division, namely by succeeding when the division of the first two elements produces the given quotient and remainder. This predicate takes its first two arguments as plus sign input arguments and the last two as minus sign output arguments. Note that it's not an error to provide numbers for all four arguments. Prolog will simply check that the division results in the values you gave it and fail if not. In general, if you supply an unbound variable for a minus sign argument, Prolog will fill it in based on the result of some computation. If you supply a variable that's already bound to a value, then Prolog will perform the computation as though the argument was unbound, and then unify the result with the value you provided. That is, a well-behaved predicate should not change its semantic behavior based on whether or not you provided a value for its output arguments. A predicate that satisfies this property is called steadfast. A predicate argument can also be marked with a double minus sign. Whereas a minus sign argument is generally considered output but may be bound, a double minus sign argument must be an unbound variable. This is used for constructors and functions that create something. For instance, the open predicate's third argument, which is unified with the stream handle it creates, must be unbound. It is an error to provide a bound value for that argument. There's also a double plus sign sigil, which dually implies the argument must be fully ground, meaning that not only is it not a variable, but that there are no unbound variables anywhere inside of it. This sigil doesn't get used as often, but it does appear in some special niche situations. An argument with an @ sign sigil is one that will not be changed as a result of the function. If you pass a variable, the variable will be exactly as bound after the call as it was before. This is generally used for type tests. For instance, the predicate atom succeeds if its argument is an atom. If the variable is unbound, Prolog makes no attempt to bind it to an arbitrary atom and instead simply informs you that the variable is unbound by failing. The colon sigil is used for meta-arguments, which are arguments that will themselves be treated as predicates or goals at some point. For example, the argument to once is a meta-argument, since once evaluates its argument as a goal in the course of evaluation. Finally, while most data in Prolog is immutable, there are a handful of data structures that can be mutated in place, and such arguments are generally marked with an exclamation mark sigil. There's a ton more to the Prolog programming language, and I've barely scratched the surface, but hopefully I've given you enough tools to be able to browse the standard library and understand the basic principles of logic programming on your own. We'll be revisiting the idea of logic programming in other languages in some future videos. But for now, tune in next time when we resume our regular schedule and take a look at Project Euler problem number 16 in Labyrinth, the maze-oriented programming language.